already approaching a time where we should start. Okay. Okay, maybe give some other people a couple more minutes. Work it out. Oh. Okay. Okay. So before we're going to start, I'm just going to tell you a couple of words about myself. Or, oh, Karina, would you want to? Okay. Okay, so hi everybody. We're meeting for a second session in the Python introduction. So for those of you who are joining us here for the first time, my name is Kasia, and I'm the president of NGSchool Society, which is a society that is organizing the NGS seminar series. And I'm a DPhil student at the University of Oxford. This is my second year. And 2 weeks ago, I have hosted a session where I walked you through the introduction to Python, which has where we covered the data types and functions, flow in Python, and it would be really good if you could, if you already have that background before joining for the Python for Data Science session. So in case you're watching this video later on and you have not watched through the first bit, please refer to the first video, which covers basically this this notebook, Introduction to Python. So this is the repository for the materials for the workshop, which is at NGSchool EU GitHub account in the repository NGS19 Python intro, because originally I hosted a session on Python introduction at the NGSchool 2019. You can find materials there. I also talk about where to run the tutorial materials, and for today's sessions, I would highly recommend using Google Colab. So you can open Google Colab, where that's not exactly how I wanted to do that. Where you would have to provide the address for the GitHub repository. And choose the branch master, choose the second notebook, Python for Data Science, and you can start following this. I will be following it, and I will be running the whole notebook in Jupyter Lab, which I host locally, and that's a good option. So cloning the repository and running the Jupyter notebook is a good option. However, it requires a few modules, and unfortunately, I have not put them yet in the setup check. So I don't know if you have them. But if you're going to be following, they are quite easy to install, or you can just skip them, because this is going to be plot9, which is port for ggplot2 in Python, and scikit-learn, where we're going to fit two models, but we can easily work with that. So without further ado, I think we can start. I will be watching at the Python webinar channel, so on Discord if you have any questions. Also, if you're following on YouTube and you have any questions, just ask them there, and people from the society will be watching and forwarding the questions here. Okay, so we're going to tackle a question of how to use Python for data science today. So what we're going to hear is this is not going to be in-depth take on every single module we're going to talk about here. It's going to be more of primer on how you can use Python for data science, and I'll show you a couple of modules that are truly necessary, but I'm not going to tell you all the tiny details about them. I'm just going to mostly tell you what you can do and show you ways how you can actually Google for help. So Python has a lot of modules. There are some that come preloaded with a Python installation. For example, OS, which provides a lot of interface to communicate with your operating system. So that will include looking at directories, creating files, and so on. It has the regular expression module. It has the mathematical module, the statistics, the basic statistics. It has a really good logging modules, which you can use for efficient logging to further help you in further debugging. And those modules come with the standard library. That means that if you install Python, you already have those modules installed. So you can just import them, which I will talk about in a moment. And there are also other libraries that do not come pre-installed, that you will have to install on your own, either within your Conda installation or with pip or in some or compile. It really depends on what's your strategy for installing modules. And they include Numpy, which is the fundamental package for scientific computing. We're going to be using Numpy, Pandas, SciPy, Matplotlib, and scikit-learn today. And those are the basic libraries that are necessary for data science in Python. But before we're going to move on to how to use them and to look at the possibilities of those modules, we need to learn how to import modules. So how to include, how to be able to use the functions and methods that are implemented in those modules. So we're going to start with the first piece of code. Basically, this statement here is the essence of the question of how to import modules. We are going to import random, and random is a module that opens up a lot of pseudo-random generation functions. So in the second line of this code, I print random integer chosen from within the set of from 1 to 19. And as you see, I imported random. And now if I want to access any function that is done by random, that is implemented in random, I just need to precede this function by the name of the module. So this is how I imported random, and then imported module random, and then from the random module, I use the random integer function by preceding it with the name of the module. However, that's not the only way I can do that. If, for example, I only want to have a certain function of interest or a couple of functions of interest from my module, I can use from syntax, which basically says that from module import functions. So from math modules, I'm importing pi and ceiling. So actually, pi is not a function because we also can import objects, not necessarily just functions. So in this example, I don't have to precede pi. Oh, actually, it's not code. Now it's code, and I can execute it. So what this allows me to do is skip preceding all the functions or the objects by the name of the module. So I can just access pi now as pi, and it's in my global environment. If, for example, I don't want to proceed my functions or my objects by the name of the module, but I want to import everything, I can just use the star. It basically will allow me to import every single function, and this will allow me to use factorial, for example. But that's not necessarily the greatest practice, because if you're going to be using a function, let's say if you're going to do from math import, like if you're going to be using a function from a specific module, it's good practice to tell your user what kind of module you're using it from. So if you want to save time, for example, and you want to type in the module, the full module name, you can also use abbreviation. You just need to mark it. So I want to import statistics module, but instead of writing statistics every single time, I just want to write ST. So I do import statistics as ST. So I'm creating an abbreviation from the name of the module. So that's basically more or less all the ways to import modules and how to use the functions from them. And now that we know that, we can move on to the first module we're going to talk in more detail about, and that's a Numpy module. So Numpy allows us, is designed to handle scientific computing. What that means is that we're going to be able to do almost like we're going to be able to do a lot of operations that we would be we would want to do when doing any scientific computing. So, for example, array operations, matrix multiplication, and so on. So we're going to work through them. This is just a warning. Please do not be scared by linear algebra here. I am using it. I'm trying to use it in a very agnostic way, in the sense that I am walking you through all the steps. I hope that none of the exercises or none of the steps we're going to follow here require linear algebra knowledge, because I try to walk you through all the steps. However, those are the best ways to show the advantages and the huge strength of Numpy project, the Numpy module. Okay, so we were talking about different data types earlier in the first part of this workshop, and we're talking of how lists are amazing because we can do all the things with the list. So kind of the way the list for Numpy is an array. So NP array, an array is the basic type you're going to be using in Numpy. And we can create an array from a list. So we create so a list has 9 elements in a list. And if we create an array from that, we will see that whenever it's printed, it says that it's an array. We can check which type of the element, like what are the types of elements in an array by typing a.dtype. And it tells us that it's an integer 64 on the base of 64 bits. We can create arrays with different types of elements. However, Numpy will try to match the type accordingly to certain hierarchy. That means that, for example, if I would put it here as B list as 9 elements, but one of them will be character, as you're going to see, it's going to be the type of character. So what that tells us is that it doesn't matter whether you have most of the elements from a certain type, as long as you're going to have at least one character, it's going to be transformed into the character. And if you're going to put, for example, a tuple inside, it will be all treated as objects. And that's the way that works best for Numpy. However, if you, for example, if you were reading in data that was coming from a user and you were afraid that someone would put in a number as a string, but you know that all of the inputs should be numbers, you can change type. So, for example, here we can type in as type and change it into float. So it's not even integer; we're changing it into a float, and then all of the and the 7 was changed into a number accordingly. Obviously, it won't work every single time, especially if you're going to have a string that will not have a number in it. So please be aware of that. And yeah, this is an important thing. So arrays in Numpy arrays have shapes, and we're kind of used to two-dimensional, one-dimensional, or two-dimensional matrices. Because that's basically one-dimensional is just a vector, two-dimensional is a matrix. For example, we can think of it kind of as a table where you have rows and when you have columns. But NumPy allows us to have n-dimensional tensors, which is quite important for machine learning. We're not going to talk about n-dimensional tensors here. I just wanted to tell you that we're not limited up to 3 dimensions. We can go way beyond that. So let's see what shape our A array has. And it has a very weird shape because we're used to looking at shapes by the number of rows and by the number of columns. However, here we only have none. And our array is of a special shape, and that shape means that it's not a specific one. So let's reshape it into 1 row and 9 columns array. So now we see that a reshaped array has 1 row and 9 columns. Okay, so let's look at a reshaped. This is how a reshaped looks like, and I'm just going to add a cell where I print A. So if anyone can spot a difference, what's the difference between a reshaped and a if they are printed out? I'm going to wait a couple of seconds. Maybe someone can write it in Python webinar or YouTube. I'm just checking whether you're listening. Come on. Someone must have noticed the difference. I'm looking at the difference between this and this array. What's different in the way they are printed? Come on, don't keep me hanging. Okay, I'm going to tell you this one. It's that one other square bracket. So that's a difference we can spot in, this is how NumPy informs us that this is 1 row, because we have one more square bracket. We're going to see that in a second. So let's compare the 2 matrices. If we just do a comparison, all the elements of A reshaped and A match, so it's all true. However, if we're going to use an NP array equal method, if we're going to use this function, it will tell us that it's they are not equal, because one of the things that this method is doing is comparing not only the elements inside but also the shape. And as we know that A is of a different shape than A reshaped. We can create the matrices from lists, and then we can reshape them. So, for example, let's say that we have a huge list, and we want to have a 3 by 3 matrix, and then we want to 3 by 3 is actually 9 elements list, but we can create. We can just create a matrix first from a list and then reshape it with the reshape function, and that allows us to create 3 by 3 matrix. And as you can see, the elements, it goes rows by row by row, because it's 1, 2, 3, 4, 5, 6. That's another row. 7, 8, 9. That's another row. We can also create a 3D array by adding this as a next additional argument. We're creating this 3D array, even though it has only one dimension, only one element. Okay, so there are special kinds of matrices that we can create. So they come in handy, for example, if you want to have a fixed matrix to which you're going to be updating, especially while you're multiprocessing something. So let's say that you have a function that will be run on multiple colors, and then you want to have one output matrix with the results, and you're going to be updating them by cell locations. So you can either create an empty array, which will have a random numbers, very, very small random numbers. You can have an array filled with zeros or ones, or any other value, like here. We can also create arrays with sequence of numbers and so on. So first, we created an array with 20, with a sequence from 0 to 20, every other number, and then we reshaped it into 2 rows and 5 columns. Yeah, 2 rows, 5 columns. So Numpy allows us to easily perform matrix operations. So for example, if we create a matrix M, which is just 9 numbers, which is exactly what we did here with a reshape. Oh, in here, a reshape 3 by 3. But as you remember from, hopefully, as you remember from your from the previous tutorial, we can nest operations. So we created this object and then we reshaped it by 3 by 3. So we have an array M that has 9 elements, 3 rows and 3 columns, and now we want to sum all the elements inside. So we know that it's 45, but we might, for example, want to sum only columns. Yeah. So that will allow us to sum columns. We can multiply array by a scalar. So that works. So every single element will be multiplied by a scalar, so by a value. So that means that first element will be multiplied by 2, second element will be multiplied, and so on. Just a comparison. This is the multiplied, and this is the original array. We can add, for example, we can add a row to each row, or so as you can see, we added a row 1, 2, 3 to every single row. So 1, 2, 3 plus 1, 2, 3, 2, 4, 6. 4, 5, 6 plus 1, 2, 3 is 5, 7, 9, and so on. And we also can add a column if we're just going to transpose our array here. And that allows us to do. So now we have 1, 4, 7 plus 1, 2, 3, which is 2, 6, 10. Okay, so those were like kind of basic examples, but why would we want to have that kind of module? Why would we want to use, for what would we want to use it? One of the examples is solving linear equations. And again, please don't be scared by the linear algebra. So suppose we want to solve the following system of equations. So we have 3 equations, 3 variables, and we have them written like this. We can first transform them into matrix form. So we have the matrix with the we have the matrix A, and then we have the matrix of variables, and then we have a matrix of we have a vector beta. We will use the Gaussian elimination and solve it on paper with the help of Numpy here. So we start with finding the upper triangular matrix, but you don't have to worry about it. I already did that. I'm just going to tell you what I did on paper and what I used Numpy for. So with Gaussian elimination, you want to get to the upper triangular matrix, and it's just a fancy name for a matrix where you have zeros below the diagonal. So in the first step, I subtracted from the row 2 4 times row first, and added 2 rows, 2 times rows first row to the third row. Then I just subtracted the to row 2, and I got a matrix which is 1, 1, 0, 0, 2, 1, 0, 0, minus 2. And now when I got the upper triangular matrix, I wanted to get the elimination matrix. And the elimination matrix is just the multiplication of each of the steps that I've made here written in a matrix form. So basically, when I am talking about transformation from this matrix to this matrix, the way I'm doing it is I'm writing what I've done. So I've subtracted 4 times row first. So I just put this -4 to the second row first position, second row first column. And if I add 2, then I just put 2. The ones on diagonal just mean that I am taking 1 row 1, 0 row 2, and 0 row 3, and that's my row 1. This row means that I'm taking 4 minus 4 rows first row and adding 1 row 2, which is what I got here, etc. So I write each transformation like that, and then I can use NumPy if I don't want to multiply arrays, especially if there's a lot of arrays, a lot of matrices that I would need to multiply. I don't want to do it by hand because the elimination, the subtraction, and addition is quite easy. However, multiplication of matrices, especially if they they grew in size, is quite complicated. So in here, I can just do matrix multiplication and get E. And now that we have the elimination matrix, we can see if this sentence here, which means that upper triangular matrix is equal to elimination matrix multiplied by matrix A. We can check whether that's true. And we can create another matrix multiplication and see whether this U matches this one. And thankfully it does. So the next step in the Gaussian elimination is that we know that AX equals B. And then we know that if we multiply each side of the equation by elimination matrix, we get this equation, which means that upper triangular matrix multiplied by variables is equal elimination matrix times the B times B. And we can write the B matrix here, which basically means that I am taking a list 1, 2, 3, turning it into an array and reshaping it into 3 columns. And then I can create an EB product by multiplying E by B. And with that, we only need to solve this last trivial set of equations. So U is 1, 1, 0, 0, 2, 1, 0, 0, minus 2, multiplied by x1, x2, and x3. And that gives us 1, minus 2, and 9 from the EB product. So we just need to solve this set of equations, which gives us this, which is the x1 is equal minus 0.25, x2 is equal 1.25, and x3 is equal minus 4.5. So yeah, so we can go into this all that trouble and use a little bit of NumPy to try and help us solve those equations, or we can just use this amazing one line, which basically will get us all the same thing without having to use a piece of paper. So that was just, I was trying to find an example that will show you what actually NumPy is good at, which is a lot of matrix operations. And you need to know that linear algebra functions with NumPy cover a lot of necessary computation for machine learning. And for example, we can use a couple of questions from the linear algebra subset of functions in NumPy to hand code our own PCA. So now I think that's an exercise for you. I would want to give you a couple of minutes to solve this before I will solve it myself. Yeah, when you're done, please type in either on YouTube or on Discord the answer for this one. If we multiply the first column of A by the second row of B, this is tell me what we're gonna get. So I'll give you like a couple of minutes to type it in. Yeah, I'm going to be typing too. If you have any problems, any questions, just let me know. If you're just going to write, you can also write like I'm listening. So that's going to tell me that yes, at least someone is on the other side. Because that's the problem with the virtual workshops, is that you don't usually know whether people are actually on the other side. Okay, come on, someone type in that you're here. Let me know that someone is listening. Come on. Anyone? Oh well, maybe no one is here actually. Okay, thank you, Tobek. -3. Okay, we'll see in a second. Shape. Okay, awesome. Arrange. Oh, shit. Oh, because it's 1R. I'm here too. Okay, cool. Nice to know that some people are here. Great. Size 5. Okay. Yes. Perfect. Now we are adding. Perfect. Hey, I hope you're doing it. Third column. Oh yeah, because again, yeah, I wanted to multiply a stage column of A by a second column by this -5, not -3. Okay, so I assume you kind of got a chance to try it on your own. Hopefully you got there, and if not, you can either look through what I typed here or in the answered notebook. There's also another exercise that I wanted you to try. However, I will leave it for you to try on your own. So this one is a bit more challenging. So in this example, I am asking you to solve a linear regression problem. So we know that the linear regression model is given by the formula that y is equal x times beta plus epsilon. Epsilon is just an error here. So the closed form solution is of that very scary formula. But what that just means that we transpose an x multiply it by x, then take an inverse, then multiply it by another transpose next, and then multiply it by y. So it looks a bit scary. However, if you're going to just think about it, all those operations, inverse, transposing, and matrix multiplication, we can just code in, we can just access a function from NumPy. So in a couple of simple steps, we can recreate the beta hat. So that's going to be an approximation of beta because we're not going to get the epsilon because the epsilon here is random noise. So what we're gonna what in this exercise I'm doing is I'm creating the data from this linear equation, and then I'm asking you to calculate, to type in this equation using NumPy functions, which include transpose, inverse, and matrix multiplication. So this piece of code will basically generate the data from this linear model. So y will be equal 0.5 times 1, which is the intercept, plus 2 times x1 minus 1 x2. And then we're creating x, in which we just put intercept. We put 1 as the first column because that will get us the intercept. And then we have x1 and x2. And as I told you, we're adding epsilon as a normal noise. So we have this model. And then in this line here, we're adding a little bit of noise. So all I want here is for you to try and succeed. Write in the beta hat, which is this equation here. It is answered, it is solved in the answered notebook. So if you want to try it at home and then get stuck at any point, just look at the answers or ask on Discord as always. Okay, we're going to go into Pandas now. So this is the second module we're going to be talking about, and that's a module that allows us to work with tables in Python. So it kind of is what data frame, dplyr, and data table a bit are in R. However, it has still differences. So if you're used to dplyr or used to data table, I think if you're used to data table, you're going to have a little bit more luck with Pandas, because I think it might be a little bit more similar. But again, it's still a separate module. So you have to learn the way to access columns and wrangle the data with it separately. So we're going to be using a penguins data set. So this was, I have to change this notebook not to use iris, given the recent controversy. And I use the penguins data set that I have taken from Alison Horst's repository. She made amazing graphics to introduce the data set as well. And the data set was the data was collected and made available by Dr. Kristen Gorman and the Palmer Station at Antarctica, a member of Long-Term Ecological Research Network. And what we have here is we have 3 species of penguins, yeah, so Anna Maria commented that random comment, there is a data table for Python too. Yes, and this is quite interesting because we're also going to be talking about the ggplot for Python, because I have my opinions about plotting in Python. But yeah, so there are a lot of there's a lot of community effort into making packages from one language available into another. However, they will come with some disadvantages in the sense that they won't always be the same. So there might be little differences between them that will come from the fact that they are written for different languages. However, yeah, if you have a favorite package that you're using in R and you're forced or you have to use Python for some other reason, you might try to look whether it was ported into Python. But coming back to our penguins, so we have 3 different species of penguins. They are taken to, I believe, 3 different islands in Antarctica. And we have information such as body mass, and we have the Coleman length and Coleman depth, and then we have the flipper length in the database, in the data frame. Okay, so we're going to be using Pandas. So let's read in Pandas. We're using import Pandas as PD. And for those of you who are following on Colab, this line won't work for you, and that's because Colab, I forgot that Colab doesn't have access to the local repository. So if you're using Colab, please copy this URL and put it instead of address for the penguins raw. Run it. It should be exactly the same because it has the commit number. So it's exactly the same data. So just please copy it and put it here. So that also showed us that as well as in this table or in dplyr in our in Pandas as well, we can just point it to the virtual address. We don't have to have the data locally on our computer. So with this line, pd.read CSV, we read into an object penguins underscore df. We read in this data, and with the comment penguins df head, we're showing what our data frame has. So we're printing 5 top rows. So we have a study name, sample numbers, species, region, island, stage, individual ID, clutch completion, date, egg, that I believe is in proxy for age. We have the Coleman length, Coleman depth, which is the Coleman depth is this, how big and how wide the Coleman is, and the length of the Coleman. We have the flipper length in millimeters. We also have body mass in grams. We have the sex, and we have a couple of other measurements that are actually not important at the moment. And as we can see, we also have NAs, which is quite good because that resembles real data quite well in that sense. So that's first way we can look up a data frame. However, Pandas comes with a very nice function that allows us to look up not only the first rows, but kind of a distribution for numerical variables. So, for example, we can see the mean Coleman length and the range from min to max through the percentiles, 25, 50, and 75. So by default, this scribe will show us the numerical. It will show us the information about the numerical variables in the numerical columns in the data set. So, for example, we also have the distribution of the sample number, which we know that it goes from 1 to 340. It goes from 1 to whatever number, 1 to 152, and we don't necessarily need the 25 percentiles here. But it did not show us the columns that are not numerical. If we want to see them, we either have to provide an option, argument for describe include equals all, or we should select the one. So in this case, because I already have the numerical ones printed, I am only interested in the ones that are not numerical. So I am excluding all the numerical columns. And I can see that for non-numerical columns, I have different options. So it tells me the number, a number of entries that are not empty. It tells me how many different unique labels I have. It tells me what's the top one and what's the frequency of the top one. So what it tells me is that I have 3 different study names here, and the most frequent one is PAL 092110, and I have 120 entries with that. It also tells me that I have 3 different species, and one species, Adeli, is actually the most frequent, and it has 152 rows, so observations. Okay, so that gives us a rough idea of the data frame in general. We can also access the row names. In here, we don't have row names because in this function that we use, PD read CSV, we didn't use an argument that will specify which one is the row name. I do not like working with row names unless I need to, so that's why we just have an index, which basically will tell us that the number of row. And when we're going to be filtering the data frame, we're going to see that we retain the information of what was the initial order. We can also access the columns, which is handy if we want to. If we have a huge data frame and we don't want to print everything, we just want to know what are the possible columns. And yeah, we can access. We can also access the values. So let's say we would want to access the numerical values of the 3 columns that I've chosen here. So column length, column depth, and slipper length. So first of all, before I'm going to go to values, I'm going to show you that if I'm going to provide a list of names to my penguins TF, I can access only those columns. So what it gives me is the 3 columns that I requested, and it also gives me the row index. And then I can access the values by just typing in values. So what I get here, I get an NumPy array. And instead of typing values, I can also try this function to NumPy. For some reason, it takes a lot of time. It should not. It should also have only one Y. But yeah, it gives us the same. And I think today, for the first time, I made a comment that we should move on from dot values and use to NumPy if we want to use an array. So that's worth keeping in mind. We can sort the values. So if we want to sort the values, we need to apply a method sort values on the penguin data frame, and we say that we want to sort by body mass. So for example, for some reason, I want to have the penguin sorted by their weight, and it goes from smallest to biggest with NAs at the end. And as I mentioned earlier, the initial row index will be kept. So as you can see, when we sort it, we know that the penguin that was put in as a 314 in the initial data frame, it is now this first position because it's the smallest, it's the lightest one. Okay, and then we have group by. So that function is actually quite interesting and quite important. So what that allows us to do is to access the data frame by groups that are created by some other column. So for example, we know that we have 3 species, and we are interested in the means of all the observations that are all numerical observations by species. So we just have to type in penguins DF, group them by species, and then calculate the mean. So again, not very informative because we have a mean for a sample number, which is not necessarily the most meaningful information. However, we also get the means for column length, column depth, and slipper length. And what we can see here, we know nothing yet about their about the distribution or about their statistical significance, but we can see that column depth might be smaller in Gento, but slipper might be larger, and Gento penguins can be heavier. We will investigate this dataset further, so we're going to see whether those differences are significant or whether the mean is skewed by outliers. But before we're going to do that, I would want you to try to do a couple of simple operations on the Pandas dataset. So we want to count, so are all species equally represented in the data frame? So what I'm asking here is, are all species have the same amount of entries per group? So yeah, so please try type it in. If you're ready, you might want to share the comment with us. So we can count values in a column with value count. So first hint is that we want to access one column, and then we want to use the value count method. If you have any questions, that's also a good time to ask them before we're going to move on from Pandas. Any questions are very much welcomed. Oh, my Python 3 kernel is very, very busy. Cannot choose tab. So the answer is that they are not equally distributed. So we have 152 entries for Adeli, 124 for Gento, and 68 for Chinstra. The next question is, are all penguins present on all islands? So first of all, let's forget about let's just assume that if we don't have a penguin on an island in the data set, that means that we don't have it on the island, which might not necessarily be true, but just for the sake of this exercise, let's assume that that's the case. So what we're interested in is we want to see we want to count how many penguins of each species we have on each island. So just we would want to group them by something, and then we would want to see the size of those groups. Okay, so if I take the penguins, and then I will apply the method grouping it. I want to group it by island, and I want to group it by species. I just need to check whether it's island or islands. Yes, island. Okay, and as I said, we can use the size. Perfect. We want to group by, did I misspell this? No. Okay, so we want to group by island and species, and then we want to get the size. And this is an interesting comment because we also could have, instead of writing penguins CF species value count, gee, Python, what are you doing? We could have also done this. We can group by species. Oh my God. And then see the size, which gives us exactly the same information. In phase, the difference between the phase one and the second one is that in the first example here, we accessed the column, and then we counted unique, like the occurrences of each unique value. And in the second one, we created a group, and then we calculated how many observations in each group we have. And the second one allows us to do more. We can group by many more columns, many more values. Okay, so we want to calculate means of all numerical variables for Adeli penguins with respect to the islands they'll live on. So one thing is that we have not yet done here, which is the filtering, which is what I'm going to show you right now, is where I have a penguins data frame and I want to access just penguins data. I want to access just the species of Adelie, I will access it as this. So what I did here is that I filtered my data frame based on the logical vector. Because if I would just show you this, that's a logical column. So I have this. So I have just entries for the Adelie. I hope I pronounced it properly. Adelie species. And what should I do now? In the meantime, I will answer Ryan's question. Could I export some table of these to an Excel sheet, for example? Yeah, you can save it to as a sheet. Like if you're, for example, going to modify the data frame, you can always save it to your drive with a specific function. You can always transform it into Excel. You can save it as CSV. You can save it as CSV. Or you can save it as Excel. Yeah, as Karen is saying, we can also use to CSV, for example. I can show you. So let's say that I want to save this one. Only. And if I go to my data directory, I have example Saivang, because it also shows how good I am with typing. Let's see. If I click it, I can look it up. So I saved it as a CSV. And as you can see, we have only 152 entries because that's a subset of the initial data frame. So let's close this. So we just used the to_CSV function, which allowed us to save it to a CSV, which is a comma separated. I have not used Excel for a while, but I believe that if I would no Module Excel. Okay, so I'm probably missing something with the installation. However, it's always better to also save it to CSV. That's going to be fine. Okay, so coming back to this exercise. So now I want to group by island. And then I want the mean. So that allowed me to filter. So the first thing I did, I filtered. And by filtering, I still kept the data frame as an object. Then I grouped by island, and then I calculated the mean. So again, so that allows us to apply methods on outputs of previous methods. That's one thing. And another thing is that if we're going to filter or if we're going to group by, it will still be a data frame, even though it will be grouped or filtered. Okay, so there were a couple of exercises. We're going to be using Pandas still for plotting. So we're not saying goodbye to Pandas, but we're saying goodbye to this brief introduction, and we're moving on into plotting. And we're going to talk about Matplotlib. So I think it's going to become evident that I don't particularly like plotting in Python in the rest of this tutorial. And especially where I'm going to be using a port for ggplot in Python here. But I think it's important to say that there are some advantages of Matplotlib, is that it allows you to customize everything. And if you would write a package that will need to draw a very particular and very specific figure, Matplotlib will allow you to do that if you can go through the documentation. But Matplotlib is the most frequently used library for plotting. in Python. So I'm importing matplotlib/pyplot as PLT. So this is also one of the functions. You can access plotting by so many different other ways, and they allow you more flexibility. However, for the introduction, I decided to use PLT pyplot because it's simplest. And I'm also using RC params because I'm just basically telling it to use a background of white color in this. It's just because I was using a dark skin, and then the plots were not printing well. But yeah, that's more advanced. Okay, so the very first thing, let's just plot a line. So what we did here, we created a plot with the 1 to 10 numbers. We added a Y label, we added the X label, and then we saw the plot. So that's the simplest thing. So in general, plot function, that's a part of the pyplot. Like pyplot set of functions has 3 arguments. I mean, you can think of it. So the first positional argument is X, and the second positional argument is Y, and then you have a shape, and you have a color, and you type in the shapes and colors as I'll show you in a second. This is a table that will tell you that if you want to have a dotted line style, you need to use the 2 dots, which has a proper name in English. I forgot now. You can use O for a circle marker, the upper G for a diamond marker, and so on and so on. And for colors, you use colors. So except for black, they all have the first letter of their colors. We can add multiple series to a plot by adding the series line by line. So we create, let's see, we create X and Y. So X is, so let's see what X is. So X is the numbers from 0 to 9. And Y is numbers from 0 to 20 by 2. And now we're going to plot them. So we're plotting X. So we're taking X as X and Y as Y, a second dimension. And then we're using red color, and then we're using dot dashed line style. And then for a second series, we're using X as the first dimension and X times Y as a second dimension. And we're using green, what is it? Dotted line style. So let's see what it is. So we have the first series, which is X and Y, and then we have a second series, which is X and X times Y in a green dotted line. Okay, so now a small exercise for you. Given a vector t equals NP range 0 to 12 by 0.5, create a plot with 3 series. First one is Y1 equals 10 times 10, Y2 equals t squared, and Y3 equals minus 10 times the remainder of t divided by 3. So I'm going to give you a hint for this one. So Y3 equals minus 10 times t remainder of 3. Okay, so having those, create a plot. Any questions about plotting so far? Okay. And I want green triangles. Look it up. Triangle was V. Then I want red dashes. Probably this. Yep. And I want T, Y3, and blue diamonds. B, what is that? No, T, uppercase. And as we can see, so the first one is the green triangles, then red dotted line, and then blue diamonds. Okay, so as you can see, we have, so first of all, if we would put every single thing we're going to add to the plot will be plotted within the cell. So because we're within the same environment, so because we're switching from cell to cell, we're resetting the plot area. Yes, exactly. So also as Caroline is saying, because we're working in a Jupyter, we wouldn't be able to see that if we would just, so let's see that. So let's make a small detour. I will start a console. New launcher. I will start a console. Import matplot with pyplot as plt. And then I will generate I will use this. Oh, numpy as np. Oh, it actually didn't work well enough. I think it might be that from a certain version of matplotlib, it will be showing inline. You don't have to do plt show, but oh well. You need to, if you don't see your plot, just try plt.show, and maybe then it will solve your problem. However, in this particular, probably it's because it's IPython. Yeah, it's probably because it's interactive. Okay, I'm gonna try one more thing to see. That's not gonna work. Yeah, I opened IPython. Yeah, I'm not gonna run Python 3 because I would have to put it in a script. However, yeah, if you don't see your plot, I imported NumPy. Yeah, if you don't see your plot, the first thing will be to try plt show to debug it. Okay. Let's do something a bit more complex, because those are very simple plots and we usually don't need to plot things like that. But we're, for example, interested in visualizing our data from our penguins. So this is one of the points why I don't think that matplotlib is as intuitive and as well organized that, for example, ggplot in R is. However, you need to know that I also don't have much of an experience with matplotlib, because by choice I don't plot in Python. Whenever I have to plot, I just switch to R, or I use the ggplot port. So in here, we want, so the task here is I want to plot the scatter plot of body mass and flipper length, and I want to color it by species. So because my species is actually a character column, I cannot directly provide it for the coloring to use it as a color. And that's why, in order to plot it with a nice legend, I need to create a loop like this. So what I did here is I have created, I used my penguins data frame to group it by species, and I iterated through those groups and plotted scatter, where I used label name of the species as a label, and that's why I was able to plot body mass as X variable and flipper length as Y variable. Or if we would want to use it with one column, we can do that as long as we have a numerical coloring column. So we can factorize it. So we can use the factorized function from the Pandas. So what it will do, it will take the species column and then transform it into a vector with the best unique value of equals 0, factor 0, second one 1, and so on. So we created this, and then we can plot it with one comment. So this is actually Kalman length and Kalman depth, and we're coloring by species factor, and we're using a data of penguins data frame. Okay, and there's also another thing. So Pandas comes with already built in some visualization methods built in, and they are all described in this link if we're going to follow it. We have the visualization. So they have linear plots, like lines. They have bar plots, box plots, I think. Yeah, and some more. And they are adding them with each release of Pandas. And you can read more about them in the Pandas visualization. So let's see how we can do that. For example, here, I want to have body mass that is normalized. So I'm not interested in the absolute body mass, but I'm interested in the normalized body mass. So I want to see the distribution of that. And I can create a box plot. I need to say which column I want to use the data from, and I can use more than one column. And I want to separate it by species, and I can specify things like figure size and specific arguments for each plot. For example, for a box plot, we can add the notch, or we can keep it as default, which is no notch. So yeah, so what I did here is the first line here, we took the penguins data frame, we grouped it by species, and then we took the body mass, and then we applied the normalization here by scaling it, by subtracting the minimum and dividing by the spread. And then we plotted it. Okay, so basically the way I approach plotting in Matplotlib whenever I am forced to plot in Python is that one thing is that if you're gonna Google for Matplotlib, as you can see, I Google a lot. You can go through tutorials, or you can look at the examples, and some of them can give you an idea for a good visualization. But if you would find yourself with data and question for visualization, you can always Google, and there always will be code available for you to help you with it. However, again, I don't like Matplotlib because it doesn't follow the assumptions of the grammar of visualization, and hence I don't tend to use it. There's also another library in Python called Seaborn. It's for statistical plotting. So let's import it. And this one is a good. This one is pretty nice because it comes with a lot of default plots that one would use when doing statistical analysis of the data. So it comes with a lot of defaults that you can just plainly use. So okay, so the warning that we're having here is because I modified the data with adding the factor species, which will which will not comply with certain assumptions of the things we're going to see in a second. So for example, pair plot here is a quite nice way to see whether we have any relationship in the data, because it will create this really nice plot where we have a column. So in rows and in columns, we have the columns that we have in the data. So we can see that the relationship between body mass and sample number. So again, this is not ideal because I added the factor here and I added the normalized body mass. However, if you look here, and we also have the sample number, but if we look at the Kalman length and Kalman depth, we can see how they the scatter plot of those two columns. We can also see for Kalman depth, we can see in the, if we're going to look for the cell which has the same column in the column and in the row, we can see the density, and they are separated by the variable we use for separating. So we can see that Gento penguins are on the lower side of the, they have the depth of the column smaller than the other two species, and with length, Adele penguins have the columns a bit shorter. And we also learned that there are some relationships in our data between different variables. And yeah, so again, so if you want to discover more about seaborn, you can look up its website. So it uses matplotlib. So it's on top of matplotlib, it allows you to use some the predefined defaults for statistical plotting, statistical data visualization. And there's also my favorite as of recently package, which is plot9, which allows us to use the syntax of a ggplot2. So if you're familiar with R and ggplot2, this code will be quite readable for you. So it follows the assumptions of the grammar of graphics, which is, so what we need to know that it's first we create a plot object, we specify the data we're going to be using, and we specify the aesthetics. So here I use body mass for X, flipper length for Y, and we're going to be coloring everything by species. Then I add a layer with geom points, and then I add a layer with the geom smooth, and then I change the theme. And I have, the only difference is that I have to enclose it into brackets. But again, it's probably very personal, but this way of writing plots is much more intuitive than the way that we generate plots in Matplotlib. And another example, this time we're going to use body mass as X and column depth as Y, and we're going to visualize a nice example of Simpson paradox, which is you can have, if you're going to have subgroups of data, you can have positive correlation, but the whole data can have negative correlation. So, and or the vice versa. Okay, so other exercises. We have two exercises, and I would want you to plot the number of each species occurrence. So what I want is a box plot, bar plot. I'm sorry, I want bar plot, and you can use whatever library you want. You can either use Seaborn, you can use Matplotlib, or you can use ggplot plot9 library to use the ggplot. So yeah. So in this case, the Matplotlib was the easiest and the fastest for me. So I just created a histogram of occurrences of each species. So this is what the information that we looked at earlier. So we know that we have 152 Adelie penguins, we have 138, I think, Gento, and 68 of the species. I'll leave the plotting the common dimensions with respect to species to you, because you can use all the different types, for example, a box plot or a distribution density, whichever you choose. It's good. There is one example in the answers that you can use later on. Okay, so this is plotting. It's not comprehensive. What I wanted you to show with this section is that there are a couple of things you can use in Python. Definitely, it takes some adjustment, especially if you're coming from R, to learn the basics of Matplotlib. If you need anything, you can always Google, you can search. There's a lot of packages that are written on top of Matplotlib that will allow you to look at the most common and most widely used visualizations. And also there are some already implemented in Pandas we can use directly as functions on the data frame. And again, Google if you need to. SciPy. So SciPy is a Python-based ecosystem for mathematics, science, for STEM calculations. And I'll just show you one example, which is Mann-Whitney test. So let's say we're going to generate numbers from the normal distribution, one with the mean 0 and the deviation 3, and another one with -2 and mean -2 and standard deviation 5. And if we plot it using box plot, we see that we see the mean here. We see the medians actually here, but we see that the distribution, we see the box plot of those two sets. Side note here, box plot might not be particularly best suited for visualization of the differences between the groups. I mean, in this case, we have only slight difference between the sizes of the two groups, but we get no information of such of that from we don't get a feeling from the plot how many observations we have per each group. However, because we have the SciPy stats, we can import Mann-Whitney test and we can apply it directly on the two sets. And it tells us that the difference is, the p-value for the difference is below a threshold of 0.01. Okay, so that's an example. That's a very abstract example. What if we have real data? So we can have a real data. We can look at the body mass. We can ask ourselves the question whether the difference in body mass between different species is significant. So we see. So this is an example of a better plot, in my opinion, better plot for visualizing the observations in different groups, which is we have the strip plot, which is kind of jittered points, and then we have a box plot. So box plot will tell us the median, the upper and lower quartile, and strip plot will tell us will show us the points, the real observations. So we see it here, and we can kind of our intuition will tell us that we kind of think that Gento penguins are usually heavier than other species. But if we want to formally test it, we can, for example, use Mann-Whitney. So in this piece of code, I will be testing for that. So for meter tools, I'm importing combinations to kind of, because I could hard code it. I can hard code the comparisons between ADALI, Gento, Chinstrap, and so on. But because I'm lazy, I imported the combinations from meter tools. So I am taking, so if I look into combinations species, just to show you what that is. Actually, penguins, species. unique. And if I look at them, I just get, okay, I'll do this. So I can see that there are tuples of Adeli and Gento, Adeli and Chinstrap, and Gento and Chinstrap. So all the possible combinations without repeating them. And for each of that pair in the set of pairs, I calculate the Mann-Whitney statistics and p-value, and I will report only the p-value. So we see that the difference between Adeli and Chinstrap, which is those two species, the difference is not significant. However, the difference between Adeli and Gento and Chinstrap is significant, with the p-values being below the 0.01 threshold. So this is just one of the examples that we can use SciPy for different testing. So if we look up what SciPy offers, yeah, okay, in a sec. SciPy library. We can look at the SciPy stats functions, which are the statistical functions, and we can see that what's available to us is quite, so we can have Pearson type 3 continuous random variable. We can generate random variables. We can create them. We can create random variables for different distributions. We can also create summary statistics, frequency statistics, and so on. So if we're looking up the SciPy stats module, we can see all the functions that are available to us, and we can see we can calculate the correlation between two variables like Pearson or Spearman, which might be interesting in an earlier example that we had. For example, here, what's the correlation between body mass and Coleman depth, and so on. Yeah. And I'm just going to touch on scikit-learn. So scikit-learn is the module allowing machine learning in Python. There are quite a lot of more modules following machine learning in Python, but scikit is the one that hosts Pca, for example, or other linear models and linear regression. So coming back to our example, our exercise from earlier, if we create random variables from a linear model, we can either, so this is the answer to that question, we can either calculate the beta hat regression coefficient directly from the closed form solution one, or we can use scikit-learn, import linear models, get access linear regression, and access the regression coefficient. So as you can see, they're the same because it's a closed form solution. If it would have been, if it wouldn't be closed form solution, it might have been different because of the different optimization methods that can differ slightly. So what we did here, so this is the way the models are created in the scikit-learn package. So first of all, you initiate the instance of an object, an instance of the linear model here. So we are creating from the linear models, we are accessing linear regression. I also wanted to specify this option for fit-intercept to be able to compare between the our multiplications and the multiplications here. Then we are using a fit method that will fit our data given x and y. And then when this will update, so this will initiate an object, and this will update an object. And with we can access the object's coefficients by typing in reg.coefficients. And we're getting exactly the same as when we got beta hat earlier. Okay, so another example, we wouldn't be calling ourselves data scientists if we wouldn't plot Pca. So let's just do that. So it's another model that we're going to be using. So in this case, because I'm interested in, so first I need to select just the numerical value, like the numerical values that I'm interested, like the variables that I'm interested in. But I also want to have the information about the species, and I want to remove all the values that are NAs. I am only interested in complete information here. So I'm creating a copy. So I'm creating a new data frame that I'll be using from now on, which is a df underscore, which is just a subset of Penguin's data frame for just those columns that I'm listing here and without NAs. Then I am, as I said, I imported some from the sklearn decomposition. I imported all of them so I can have access to more like MTS, etc. But I will be using Pca here. So I am creating a Pca object, and I am specifying already that I'm interested in first two components. Then I am fitting my Pca object. I am dropping the column species. So that's because species is a categorical character variable, and I just need the numerical variables here. So I'm just dropping this one column. So I'm fitting my Pca model by the numerical variables, and then I create a projection from the Pca. So I created a Pca model, I fitted my data to the model, and then I transform my data here. What I'm doing here is I'm creating a subset that will be that I will be using for plotting. So I am creating a Pca plot data frame that concatenates the projected data and the species, and I also rename the columns. And as again, because I want to color them by species, I am creating a loop here, and this is my projection of the Pca. So I created a Pca model, I fitted my data, and I created the projection, and then I was able to plot my projection here. So I plotted the data that was, so I plotted 4-dimensional data, which was Coleman length, Coleman depth, flipper length, and body mass into the 2-dimensional space of the PC1 and PC2. And I can kind of see that this, so Gento penguin might be a separate group from Adelie and Chinstrap, but the separation between Chinstrap and Adelie will be a much harder task. Okay, and I can create the same plot with my favorite Python plotting library, which is plot9. It's just much easier that I don't have to create a loop to plot different, to color by different species. Okay, so that was kind of an introduction to the scikit-learn module. There are many more models that we can use from the scikit-learn library. We can also use many more other projections, like MGS, for example. And now I think we should try doing the exercises. So the exercise is to build a model that will predict the size of a flipper based on a penguin weight, and we want to plot the prediction against true values. So those are the two last exercises, and for those of you who are actually following, I will give you a bit of time to try them on. And if you have the code that you wrote to generate those, please share them on Discord or on YouTube, and I'll give you like a couple of minutes. And if you have any questions, you may ask them now. Would be a good place to ask. In the meantime, I would want you to work on the visualization and build the model. And I'm really interested in which models you can you'll start. A hint is that given the earlier plot that we saw, because we're looking at a model that will predict size of a flipper based on penguin weight. So we want to know the flipper length based on body weight. So let's see how that, actually, we don't have to go there. We can just plot this. Penguins toe to PLT scatter. So it's body mass grams and flipper. We're getting into dangerous territory where I have to spell things. Flipper length. And we're going to be using penguin CF. And before I'm going to do that, I need to look up what kind of columns I have. Penguin CF. And I have species factor, so I can color by species factor. So as you can see that I think a good start will be a linear model, given that there seems to be a linear relationship between the body mass and flipper length. So I would start with that. You can look up how we created a linear model for the previous example. So we can use linear regression to predict. And maybe to make things easier, I would want you to provide an answer for the question: how long will a flipper be of 7,000 grams? What will be its flipper length? So since we already imported them, we don't have to import it, but you can copy this. So from scikit-learn, I import the linear model. I create a linear model, maybe to penguin flipper. And I have to fit. So my X will be body mass. Okay. It's going to shout at me, but I'll show you how to get rid of it. Flipper length. I'll split this. Okay. So let's keep the plot here. So now this is going to yell at me. There will be warnings, so don't worry about it. So we're creating a penguin flipper model, and then we're trying to fit it. However, it is complaining because it has expected. So reshape your data either by using array reshape if your data has a single feature, or array reshape if it contains a single sample. So in this case, we have a single variable. We have many samples, so we have to first bring it to a NumPy array. Okay, NumPy, and then we want to reshape it, and we want to have -1, 1. And now we were able to fit linear regression. And now we're interested in prediction. So given, oh, it's going to complain again. All right. -1, I think. Hold on. Perfect. Equals empty. 7,000, and we want to reshape it into -1. So it predicted a length of 326 millimeters. But another point of our question was to plot the predictions alongside the true values. So let's do that. Let's do scatter. And as X, we're going to use CF flipper length millimeters. And as Y, we will use penguin flipper predict. And we want to have no, body mass. Body mass grams to NumPy. Oh no, this we don't have it. I know we have it. Because it's okay. Okay, to NumPy reshape -1, 1. And we see that the predictions are, there is a positive correlation between the actual true value and the predicted value, as we can see here. So what we did here, we initiated the linear regression model. We fitted our data into it, and then we use it to predict and check how well the prediction of the flipper length it is given the body mass. It is not perfect. However, it is what we would, there is a positive correlation, so that's some sort. So as I mentioned earlier, we had access to SciPy stats thing. How did we import SciPy stats? Because we can check how good the correlation is. So we just, from SciPy stats, we just imported. So from SciPy stats, import Pearson, and we can check the correlation between those two. Okay, where did I make a mistake? Pearson R. And we see that correlation is of 0.07, and there's the p-value for the correlation. Okay. Are there any questions regarding this part? Yeah, I don't like the virtual tutorials, to be honest, because I don't know. Are you still there? Am I talking to myself? Probably. Okay, then I'll make that another example as well. So this is another question. So we saw that we know that there are three species in our data, and we're interested in can we. So let's say that given our 4 variables, Coleman length and Coleman. Okay, good. Nice to know that you're still there. Thank you, Adrian. So we know that we do have 3 species, and we want to see whether given the flipper length and the Coleman information and the body mass, we want to see how well we can cluster them. And since we know that we have 3 clusters, and we just want to an easy example, we can use k-means clustering. So I linked sklearn cluster k-means to this. So if you want to, you can look up the code for fitting a model. So again, you have to initiate. Okay. So we need to initiate the model. So first, we need to, of course, import it. We need to import sklearn. We need to import k-means. Okay. Then we're gonna create an object, and we want to see what are the options. So okay, so we're gonna have 3. We know that we have 3 clusters, and for initiation, we're gonna say 0. So we created a k-means. Now we have to fit our data. Fit, and we're gonna take the drop Pc axis 1. That's what my df underscore is. Yes, okay. Okay, df drop, and then to numpy. What are you showing with? Oh, random state. We wanted to random state. We didn't want to init. Yeah, because init is a question of where to start, like which points to choose as an initiation, and we're going to start in random state. We're going to choose as random state equals 0. Which tells us determines random number generation for centroid initialization. If we're going to set it to the same number, we should have more or less the same setting conditions. Okay, we fitted it. And now we want to see what are our labels. Okay, so we see that we have 3. We got 3 clusters, and then we got labels for each observation in each cluster. So we want to see how well we did separate them in comparison to species. So we can create 2 plots, one side by side. First one will be PLT scatter. what should we take? What was the best in showing the separation? Oh, we can do the Pca projection. Why not? We should use it for visualization. Where was my Pca? Really forgot most of it. Oh, Pca to plot, wasn't it? Yeah. Oh, this is my, okay, cool. Pca plot. Okay, I'll copy this. Goes a little better. And I can do subplot 1, 2, 2. Pca groups. Plot group by species, and the other one will be groups 2 equals Pca plot group. Pca plot group by label, but first we need to add it there. So Pca plot label equals King's label. Let's go up. Now I need to scratch that. I'll start again. I cannot do that. Why? Because I have chosen different data for Pca and different data for k-means, so I cannot use this for plotting. But doesn't matter. Species factor equals PD factorized TF species. So that's the first thing. Now I'm creating a subplot because I want to have them on side by side. So one column, one row, 2 columns, first instance. PLT scatter, and let's say body mass grams, slipper length millimeters, C species factor, and data TF, PLT subplot 1 to 2, PLT scatter, and this time we're going to do the same plot, but instead of coloring by species, I will color by k-means labels. I'm lucky enough it's going to work. It didn't. That does not work much. So I have DF species k-mean labels. PD factorized. Okay. You're yelling at me here. Quite tired. Okay, of course, of course. Of course, honey. So as we can see, the labels did something. They not necessarily recapitulated the species segregation, but it did show us that it basically cut is basically cut into 3 different groups based on the body mass. So not ideal. Definitely seems ideal. What if we look at the Coleman? Where was the best separation of? If we go back to this Seaborn plot, which one was the best separation? Maybe this body mass and Coleman length. So let's see, Coleman length and body mass. Yeah, I guess it did cut. It basically came into separating based on the body mass. It split it into 3 groups, mostly because of the body mass. So again, not ideal, but at least we know that k-means won't work here. We would need to find a different way to classify our data. Okay, I think with this, I will conclude this part of the notebook. Again, I'll highly recommend you going through it on your own. The answers are saved in the answered notebook. And again, if you have any questions, you can always ask on Discord. And yeah, we have still 3 more minutes for questions. If you have any, just shoot. I'll be here on the other side of the computer, hoping that someone is on the other side of the internet. Yeah, but my biggest advice about plotting in Python, which is probably unfair to Python, is not to use it. If you can, just use ggplot because it's brilliant. For now, I think it's the best. Well, silence just. They say that if a person cannot sit silent with their thoughts, that's not a good sign. So. Okay. Okay, I think since there are no questions, I will conclude. Again, if you have any questions, you can ask on YouTube or you can ask on Discord, and I'll be checking it. So yeah, thank you very much.